you all once again to be here, and we try to get some good points again. Okay, so let me try to say, if you let me try to recap a few some key points about this thing. Okay, what are we going to handle in this is in the conventional quantum field theory, which talks about three different kinds of fields, quantization of three different kinds of fields: electromagnetic field or electromagnetism, electroweak theory, and the strong interaction of the QCD theory. So QED, QCD, and electroweak theories, these three theories. And they talk about the zero-dimensional point particles, describe everything in terms of zero-dimensional point particles. So, for example, the boson fields or the fermion fields, they are zero-dimensional. In string theory, what we want to do is we want to describe our boson fields or the fermion fields later on when we talk about superstring theory through one-dimensional fields, through one-dimensional objects. So what we want to do is, you see, we have introduced a function, some object called x nu of tau, where these are the coordinates, x nu are the coordinates, and through this we wanted to describe so-called D-Brane action, where tau is a parameter and x nu of tau embeds the word line into the space-time manifold. Okay. Now we want to have tau and sigma just on parallel lines with this, and with this we would describe D-Brane action, and here for the D-Brane action we would have so this is a world sheet. This is a one-dimensional object. Here, this is sigma, and this is the flow of tau. Instead of this, I could even have a if I have a closed string here, this is an open string. When an open string propagates in the space-time manifold, it describes a open world sheet. When a closed loop or a closed curve or a closed string propagates, it sweeps out a tube. So this is the world sheet of a closed string, a cylindrical kind of an object, or a tube kind of an object. Here, in this approach, what we are doing, when we have a field phi of x mu in our conventional field theory, or a mu of x mu, the electromagnetic field, or let us say the Dirac-Spinner field, okay, as well as their canonically conjugate momenta, they will also be fields. So in conventional, this is QFT, and here we want to replace them these were zero-dimensional fields. Okay, this is a boson field, this is a fermionic field, and this is a vector field, right? And now we have, so we want to describe by one-dimensional strings. Okay, this is the main difference. We have introduced an extra spatial coordinate, okay, in addition to tau. And then we would like to see or construct the, so you need the action to define a theory, and we would like to understand each and everything about the action and what kind of a metric we are using, and that should define our problem. So another point which is important here is that each point on a word line, each point is an event. Each point is an event. The same thing is also true for a word sheet, whether it's open word sheet or tube closed word sheet. So, like this for the open string. So, you see, this is only, this is the string, okay, in any shape, whether you plot it like this or like this or like this, you see all of them are topologically equivalent objects, because one can deform into the other. Similarly, if you make a closed curve like this or like this, or they are all topologically equivalent, so it does not matter in which shape you plot them, in which shape you show them. Okay, they can always be continuously deformed into the other shape. Okay, so here also each point on the word sheet also corresponds to an event. And in relativistic context, instead of talking about the square of distance between 2 points, we talk about the square of the interval between 2 events. Okay, and that is what we denote by ds square. So this is as long as v is less than c. Okay, and for ds square we could write minus eta mu nu dx mu dx mu. Okay, and now I could also write this as minus eta mu nu dx mu over del sigma alpha mu over d sigma beta d sigma alpha d sigma beta, and I could now define this object by some g alpha beta, and therefore I could write it as minus g alpha beta d sigma alpha b d sigma beta. Now let us look at the physical interpretation of these two lines. What is the meaning of this line? So eta mu nu measures distances. Distances we loosely say distances always means the separation of the intervals. Okay, so this measures the separation of two events in the space-time manifold, which we call as target space, and g alpha beta measures distances on the word sheet. In the word sheet space, g alpha beta is also a metric tensor, and it measures separation in the word sheet space of the distances between the. So this is a new measure that we have introduced. and this is defined in terms of this, and this G alpha beta is called as the induced matrix on the word sheet. Yeah?
When
Yes.
sigma and x are connected by a Lorentz transformation, aren't we back to classical GR?
Yes.
Okay,
Yes.
that's
Yes. And why is it called induced? It's called induced because this G alpha beta is defined in terms of, or is determined in terms of eta nu, the metric tensor of the background space. Therefore, this G alpha beta is called as the induced matrix. Okay. So this is one aspect that we need to understand. And the second aspect is related to the just elementary definition in the differential calculus of the differential element dA. This is given by minus in any space which is defined by a metric tensor G alpha beta, or whatever we call it, then this is the definition of the differential area element, just using simple differential calculus. Okay, and by doing this, we have seen that the action in the relativistic point particle was proportional to length of the distance. Here, for that was zero dimensional object, and here the action is proportional to minus dA, where dA is your this element, so it is due to sigma. Okay, so the mass is to be replaced by the tension. This is not a derivation, it's just a generalization. This is how we intuitively go from simple zero-dimensional objects, point particles, to the one-dimensional strings. Okay, this is one more important thing, and this is actually d to sigma is an integration over d tau and d sigma of G alpha beta, and this is your famous Nahm-Rugger action for the one-dimensional strings or the string theory. So all such actions which involve square roots are called as Nahm-Rugger type of actions. We could have more fields into the theory later on at some point. Right now we are interested only about the so-called string coordinates x mu, which are kind of scalar fields. So let me try to show this. This is another key point, how we go from conventional field theory. So to write the action of a string theory. Okay. So what we do is, in field theory, what we do is, action you write as d4x. For example, 1/2 d mu or d alpha phi minus 1/2 m square phi square. And you would write the same action as also as d4x minus 1/2 of del alpha phi minus 1/2 m square phi square. This is, here you are using the sign signature as +1, -1, -1 and -1, And here you are using the signature -1, +1, +1 and +1. Is this okay? So that this term is nothing but the kinetic energy term for the scalar field phi. And the kinetic energy term has to be positive. Okay. So if you write it, for example, this is in 4 dimensions. Okay. In 4 dimensions. Now if I write it in 2 dimensions, I would have d2x minus 1/2 d alpha phi minus 1/2 m square phi square. Let me stick to this convention because in string theory we would be working with the convention of sign convention of -1 +1 and so on. We are in 2 dimensions. Okay. All right. So, and supposing let me drop for the time being mass term for the scalar field, so that I am talking only now about 2-dimensional massless scalar fields, and they are real scalar fields. Okay. I'm trying to take you to the generalizations for the Polyakov axiom. So this is okay. You see, if you write it in the component form, what will you get? d2x, and if you expand it, this would be minus 1/2 into, this would be phi dot okay, let me write it term by term. Let us just see one term. Okay, del 0 phi plus del 1 phi. Let me drop the mass term. Okay, I have dropped the mass term, and now using this minus plus convention, when I take it downstairs d0 phi, I will get a minus sign. Okay, and here I will not get a minus sign. So d1 phi, and what is this term? This is equal to d2x into 1/2 phi dot square minus 1/2 minus plus minus 1/2 phi prime square. So whether you go from here with this sign convention or you go from here with this sign convention, you will always arrive at the same result. Okay, you will arrive at the same result. So which means this is the phi dot square is the velocity square. So this is the kinetic energy term, and so I should have the kinetic energy term positive. That was the reason I flipped sign here and I flipped the signature of my metric tensor. This is what we are doing, conventional real scalar field theory. Now we want to generalize this. So if we want to, so this, and also this is in a flat space time. Okay, in flat space time, all these theories, they are linear field theories. Linear field theories. Supposing you want to write the same theory in the background of a gravity, what would happen? You would have a curved space time, non-flat space. And what will you do? How would you construct that? So in the same, if I go to curved space time, okay, then this would be d2x into square root of the minus g. G is the determinant of the metric tensor. Okay, and then I would write minus 1/2 d alpha phi. Okay, so I would write it as beta and g alpha beta. Okay, now this is my 2-dimensional real scalar field theory, massless scalar field theory. However, in the presence of a gravitational field. Okay, so my invariant volume element d2x goes to minus d2x. Okay, and I want to replace phi by, as I said at the beginning, I would like to replace this. So this is phi. Phi is a function of x mu. Now I want to go from field theory to string theory. And so here I want to, this is also a scalar field, this is also a scalar field, this is a zero-dimensional scalar field, this is one-dimensional scalar field. Okay? And so here, this is a function of sigma. Is this okay? This generalization is okay? So, therefore, I can write this as, now, this is not really, this is not equal to this, but I am writing that, generalization. Okay? So, I would have d2 sigma square root of minus, let me write h for, I write here, h is equal to determinant of h alpha beta. H alpha beta is my two-dimensional auxiliary field. Okay? Alright. So, essentially gravitational kind of a field. So, I would have this, and h is, and now this g alpha beta. So, I have h alpha beta, and I have minus 1/2, and del alpha x mu del beta x. So, x mu. Okay? So, phi, I have, if I have a, if I have the product of phi, so for example, phi square, I would replace by, okay, this is the sort of x square. Okay? All right. And this I could then write as let me take this minus 1/2 here, and this actually, it always, one could say that it goes like this, okay? Or here also one could say that it goes like this, okay? So here I could put a vector of string tangent and h alpha beta, and now I could write del beta x mu eta. And this is then my proper Polyakov action for the string theory. You see, so do we start getting some feeling for it? What kind of generalizations are involved? You see, we always have to remember this very most fascinating topic for me, how we go from classical mechanics to classical field theory.